All right, this is our last real substantial lecture of the term. And today we're going to talk about a class of problems which form an excellent application of calculus. One of the important ones are called optimization problems. And they're so important that, for instance, other universities, which I've taught, they have entire classes that will cover the topic that we're going to do in the next 50 or 60 minutes. So, it goes without saying then that we're not doing everything. And yet I said it. All right, so you're going to notice today that the way we work these problems is very similar to another class of what I call world problems, namely related rates problems. Right, so you're going to see a lot of derivatives of letters with respect to one variable, and then maybe do some implicit differentiation, move things around, take a couple of different equations and mash them up with each other and compare them. And, okay, same sort of idea. But whereas with related rates, we were really thinking about the chain rule all the time. With optimization problems, we're mostly thinking about the first derivative test and the second derivative test. So remember what the first derivative test we're talking about as well. You take a derivative, right, and if it's equal to 0 at some point, and you go to one side and it goes down, and you go to the other side and it goes down, right? So it meant that on one side the derivative was positive, then it was 0, then it was negative. Then what did you have? You had a local max, right? Or conversely, if you, alternatively anyway, if you went down and then you went up, you had a local min, right? And you tested this using the first derivative test. So what optimization problems are doing, well, you're trying to optimize something, which means you're looking probably for some max or some min. So let's just jump in and do a problem, okay? And it should come out pretty easily what we're looking for. So when you work one of these problems, you're always going to have either something you're trying to maximize or try to minimize. Okay? And then what makes these problems interesting is that you usually have a constraint. Okay, something that you have to keep into account that you can't get around it. You just have to do it. So you can either maximize or minimize, and then we're going to have a constraint. And you have to know what those things are. M and C. Like, are you guys too young to know who MC Hammer is? No, you know, what's his song?
Hammer Time.
Hammer Time. Oh, no, the most famous one, right? You can't touch this. You're right. That thing. Exactly. These don't really work as parachute pants, but okay. So you have MC, right? Like MC Hammer. You can't touch this. That's a constraint. You can't touch it. Okay. Okay. So let's do a problem. We'll figure out what these are in that problem. So, what's a good problem? Okay, so let me start off with a variation on a typical optimization problem. All right, and if you've taken calculus before, you've probably seen the more basic version of this. Okay, let's draw a river. And you're going to build a farm. Okay? And it's going to be a nice rectangular farm. And you only could get a loan for a certain amount of money, and you can only buy a certain amount of fencing. Okay, and so you buy this fencing. Okay, but you don't need to fence off the river because you're not worried that anybody's going to be stupid enough to jump into the river. Okay. Okay, and so you start off by saying, okay, say that's the length of this side x, right? Same as this side, and the length of this side. Okay, and the very first problem that you always try to do is say, okay, fine, how can I maximize the area, right, of my farm, given the constraint that I only have so much fence? Okay, so I want to maximize my area Right? Of course, the area of a rectangle is just x times y. Okay, so in this case, I'm maximizing. And my constraint is the amount of fencing I have. Okay, so in this case, right, well, the amount of fence that I have is going to be, well, x plus y. Okay, 2x plus y. And so let me say the total amount of fencing I'll call L. Right, for length of fence or something. Okay, so I only have L amount, and however I make, whatever I make x and y, right, 2x plus y has to equal. And I can't touch that. Okay? Okay, but now here's the thing. That first year, you put all your animals on the farm, and, well, you see, there's nothing separating them. And so they end up, you know, killing each other. And it's really, really sad, and you lose most of your livestock, you know, that go over and step on the eggs of the chickens, and it's just an absolute mess. All right? And you lose basically all your money the first year. Okay, so this isn't a very good problem then, because if you did this like this, right, your farm would go under. So year 2 comes, and you say, okay, I saw Charlotte's Web. Okay, and when I watched that movie, okay, what did they have? They had little pens for all the different animals, right? There was more fencing in there that did things. So you say, okay, maybe I should do something like that. Maybe I should fence this thing off and partition it. Okay, and then I make a grid, and now I can put animals into different components, and now they're not going to kill each other or, you know, just ruin each other's areas, and my farm, maybe I'll have a better chance. Okay, so here I've drawn a specific number of lines, but let's just say in general that you can have any number. And so let's say that is equal to the number of vertical fences. Okay, and when I say a vertical fence, I just mean fences running away from the river. And n will be the number of horizontal fences. Okay, so a slightly more realistic problem. But now this is going to change my constraint. Okay, I still only have a certain amount of fence I can put in. Okay, but on the other side, now it's not just 2x plus y. It's actually, well, x's do I have? I have exactly as many as I have vertical fences. So my 2 is m. Okay, I have m x's. And now instead of just having the 1y, I might have more. Okay, here I have 3, but I could have more. And n is the number of those horizontal fences, so I get n times y. Okay, so I have a new constraint. Okay, and this is now much more interesting. Which you probably haven't seen, even if you took calculus. Okay, but the way we solve it is going to be exactly the same. Okay, so what are we trying to do? We're trying to maximize this function, right? Or the area given, right? This. Okay. Well, how do you maximize some function? Right? How do you know when you found some sort of a maximum point? How did we find maximum when we did curve sketching?
The derivative was 0.
Yeah, exactly, right? We looked when the derivative was 0. We looked for critical points. Okay, well, let's try that. Let's take the derivative area and set it equal to 0. Okay, now we already have a problem when I do that. I want to take 0 and set it equal to the derivative of area. But what do I take it with respect to? Well, it turns out you can just make a choice. All right, it makes sense to use either x or y, but which one, right? And there's symmetry to this whole problem, so it really shouldn't matter which one you choose. So how about we choose x? Okay, but we can choose y. Okay, so of course the derivative of a with respect to x is the same as the derivative of xy with respect to x. And we have to use the chain rule to do this, and the product rule. So first, if we take the derivative of x and fix y, then we just get 1 times y plus we fix x, and we take the derivative of y, right? Which is just what? What is it? Y prime. Right? Remember, y is a function of x. Okay? Because the L over here is a fixed number, we could actually write y as a function of x. We won't do that here, but we could. Okay? You can't. Once you specify what x is, that actually tells you what y has to be. This is actually dy dx, right? Or y prime. Okay? Well, can we actually figure out what dy dx is? How could we do that? Well, look over here. We have another formula we can use. We have our constraint. Okay? Remember, L is some fixed number. It's just a constant. So what if we took the derivative of this expression with respect to x? What would we get? So let's do that. Let's make a little room. We'll do that here. If we took the derivative, right, of L, of course this would be 0, because L is a constant. Right? L is fixed. It's our constraint. On the other hand, this is equal to the derivative of mx plus my. Okay. Well, m again is constant, so the derivative of mx is just m. And the derivative, well, n again is a constant, so of ny is going to be n times derivative of y, right? It's just dy dx. Okay, so 0 is equal to m plus n dy dx, which implies that dy dx equals, subtract the m, divide by n, minus n over n. Okay. You can plug that into this formula here now. Y plus x times minus m over n, so that becomes minus, no parentheses, minus m over n times x. Okay? So y minus m over n times x equals 0. I can solve for y, and I get y equals m over n x. Or if I want to get rid of the fraction, multiply both sides by n, and I get n times y equals m times x. Okay, so what does this tell me? Well, what I would like to tell me is the following. If I choose x and y such that n times y equals m times x, then I will maximize the area given the constraint that x plus ny has to equal. Okay? And that could be the case, because when this condition holds, we knew that that meant the derivative was 0, which meant we had a local what? If the derivative was 0, we get local or minimum. That's the problem, right? How do we know that this condition doesn't actually tell you the minimum area that you can get? Right? Remember, the minimum can happen at a critical point. Right? Well, we had another test that told us. Right? How did we know whether we had a maximum or a minimum? Well, one way is you could look at points on either side and look at whether it went from positive to negative or negative to positive. But there was another test, a second test, right, which was the second derivative test. It said you take the second derivative and look whether it's positive or negative. If it's positive, you have a minimum. If it's negative, you have a maximum. Okay. Well, let's just check really quickly. Okay. So this was our derivative. Okay, the derivative was y minus m over n times x. Okay, so what's the second derivative? The second derivative is, again, just the derivative of the first derivative. So it's the derivative of y minus m over n times x, which is equal to, well, the derivative of y is dy dx, minus derivative of m over n times x is just m over n. And dy dx was minus m over n. So minus m over n minus m over n, so e minus 2 over n. Okay. Is this positive or negative? Well, what are m and n? These are numbers of fences, right? So those are certainly positive numbers. Okay. So everything is positive, and then you have a negative. This is a negative number. So the second derivative is negative. Implies this actually gives you a maximum. Okay. For instance, if we go back to the case where we just had year 1, right, just the outer border. Okay, so then the number of vertical fences was 2, and the number of horizontal fences was 1. Then this would tell you y should equal 2x. Okay, so that would tell you that, right, this y should be the length of these x's. Right, if you want to maximize it. And if you specifically how long they should be, well, I need to tell you what the constraint L is. Okay, and that's 2 equations with the 2 unknowns. Okay, so here's what we did. We start with a problem. We want to maximize or minimize something. We have a constraint. Okay? And then what we're going to do in all cases, right, is take derivatives of both equations with respect to one of the variables. Right? Usually you get to make a choice. You make those derivatives, right, and where you want to maximize it, right, you set that equal to 0, because then you're looking for critical points to find maxes or mins. Right? Then you're usually going to use the derivative of the second one to help plug in, right, another value. That's when you have 2 different derivatives. That's going to help you out. And then you're going to be able to solve for some condition which tells you have a max or a min at that point. But to decide a max or a min, you use the second derivative test, right? And check whether it's negative or positive. All right, now I'm leaving out a lot of technical things that pop up. Okay, there's a lot of cases that you have to deal with potentially. Okay. We don't have to go into all those, but if you look into the lecture notes, you can find them. Okay? There's these things explained in gory detail, including a lot of references to the extreme value theorem. Okay, which I very quickly recall what that was talking about. Okay, so let's say I have a function, a closed interval, right? So I include the endpoints. And I'm looking for an absolute maximum minimum. Okay, not just a local one, but really the highest on an interval. So let me draw a picture. Okay, so let's say I fix a point A and I fix a point B, right? Give me my closed interval, A, B. And I draw some. I'm looking for the absolute maximum. What the extreme value theorem says is as long as you have a nice continuous function on this interval, then you're either going to get, well, first there will absolute max, and there will be an absolute min. Right? And what you see is that it's either going to be one of the local mins or local maxes, or one of the endpoints. So for instance here, you have a max, but it's not an absolute max on this interval, is it? Why? Because, well, this point is higher, one of the endpoints. Okay? But the absolute max is always either going to be one of the local maxes or one of the endpoints. Okay? And the absolute min, the same thing. Well, this is hard to tell visually. Right? There's a local min, there's an endpoint which is also quite low. Right? And then you'd have to check points. Right? You have to actually say, okay, which one is. In most of the problems we're going to see, there are going to be natural defined endpoints. For instance, right, can x and y be any real numbers in this problem? Considering it's a real-world problem.
Greater than
zero. Right, they have to be greater than 0. It doesn't make any sense, right, when these things are negative numbers. Okay? You could allow these things to be 0, but then, of course, what's the area? It's going to be 0 area. Okay? So, it's fine. Allow them to be 0. Okay? The exclusion theorem says if you allow the end, okay, then you either have local max and mins or the endpoints. Okay? But it's okay to allow that endpoint where one of these is 0 because, heck, you know that's not going to be a max, right, when the area is 0. Okay, so it's no skin off your nose. Okay, so let's look at another example. This one I find quite nice. So I don't actually want to erase that. So this one, I can tell you already what we're minimizing. So let's write minimize up. Constraint. Okay, and like almost all good optimization problems, this one has a river. Okay. There are 2 towns, and they decide to build a plant, and it's going to convert water into energy. Okay, and by converting, maybe get some water wheels or something. They're going to get their energy from this river that's going by. And they decide we just really want to build one power plant for the towns, right? There's no sense in each town building their own power plant down by the river. Okay? Of course, they have to getting the energy from the river, right, from the power plant to the cities. Okay? And the question is, where should they put it? So let's say one of the towns over here. Okay, this will be town A. And I have another one over here, and this is. Okay. And let's say from the beginning, this is a typical optimization problem, that they're the same distance from the river. All right. Where should they put the power plant? Well, certainly in between them, right? That makes the most sense. Where should they put it? In the middle. Okay, that's the intuitive idea, right? The problem is symmetric. Okay, so if you were to move it one side or the other, how could that possibly be the right answer? Because if you reflected the whole picture, then, right, it should be the right answer, right? So that has to be the right answer. Just put it right in the middle. Okay? And if you use calculus, all right, to analyze the situation, that's exactly what it will tell you. You already knew you should make it as even as possible. Right? Stick it right in the middle. Okay, so this is a good problem, but not very interesting because you could probably figure it out. So let's change it up. Okay, let's make it more interesting. Let's say that town B is farther away. Okay, town B is now farther away than town A. Where should we put it? Right, this now becomes an interesting problem. It's not as clear. Where should we put it? Okay, so well, it's going to go somewhere. Put it here. Okay, lay the pipe. Oops, we missed. Okay, and then we lay some more pipe. We gotta know what these things are. All right, so let me give some names to what's going on. Let's see. Well, since this is, say this distance to the river is A, and this distance to the river is B, and the length of the from A to the power plant is going to be L1. From B, it will be, let's say L. L1's fine. It will be the distance from. And let me see the name to the other distance here. Yeah. So the name to this whole distance. So the distance horizontally we'll call W. And the distance from A to the power plant, x. What do we call the distance from this point to the power point? Well, if that's x, then that should be y. Well, we need to give a new name for this because we actually already have w and x, and that's w minus x. Okay. No need to waste variables. Try, well, what are we trying to minimize? We want to minimize the amount of pi away. Okay, that's L1 plus L2. We want to minimize. And, well, let's say that L will be their sum. Okay, we want to minimize equals L1 plus L2. Okay, and what is our constraint in this case?
The distance between the power.
The distance between
like
the power
x and minus x.
Yeah, well, certainly this W is a constraint, right? We can't change that. We can't change these distances. Okay. So let's just write down what we know we can't change. Okay. Sometimes it's easy to figure out what's my constraint. Okay, the clear. I have a certain amount of okay. Well, let's say here we know that is fixed. We know that A is fixed. We know that B is fixed. Can't change those. Okay. X and W minus X. W minus X will change when X. So X can change. Okay. Now, eventually we want to take some derivatives, but to take derivatives we need some functions up here. What kind of function is going to run? I mean, what do I know from this picture? Right? For instance, triangles. So what kind of functions could I write down? I could use the Pythagorean theorem. What does that tell me? Well, for instance, a squared plus x squared equals L1 squared. L1 squared equals a squared x squared. And over here, let's see, b squared plus x squared equals 2 squared. So L2 squared equals b squared plus w minus x squared. Okay. Okay, well this is so bad because, well, I minimize L, which means take the derivative of L with respect to something. But L is L1 plus L2, and I need a couple of formulas that tell me something in L2. The derivative of L is the derivative of L1 plus the derivative of L2. Well, maybe I can do this a little bit. Let's see what we can do. We'll mess around when we get something nice. So first, because it's an optimization, we're going to minimize something, we're going to take a derivative of L with respect to, well, what do I get? What's the variable? X, right? That's the only variable. Okay, this is fixed. Once I know X, I know W minus X. Okay, and X is just how far the power plant is this line. That's what I should take the derivative with respect to. And I want to set it equal to 0. But now I don't know anything about L other than it's plus L2. So this is the derivative of L1 plus the derivative of L2. Now it's bad because I don't know what the derivative of L1 and the derivative of L2 are. So where do I go? I can go over here, right, and use these constraints right here, right? Constraints. So I take derivatives of my constraints. So the derivative of L1 squared is the derivative of a squared plus x squared. Okay. What's the derivative of L1 squared? 2L1. L1 is a function of where I put the power plant, right? L1 over x. Right, which is good because I need to get some formula that has dl1 in it. So dl times, I have 2l1 times dl1 dx. Okay, equals, well now the other side, of a squared. What is a? A was a, these weren't just constraints, right? That's a fixed right there. Okay, so I just get a 0 squared, and what about the derivative of x squared? Derivative of x squared with respect to x, just 2x. So dl1 over dx is, I just divide. And I get x for L1. Okay, so I've got the first part. Yeah.
How did you get the last the dl1 over dx?
This?
Yeah.
I have d2L1, d1 dx, d2 divide,
Okay.
cancel the 2's. All right, let's do, well, we have another thing to do, L2 squared, right? Because we need dL2. So the derivative of L is the derivative of B squared plus W minus X. Okay. Differentiate this second equation. Okay, on the left, well, it's the same thing, right? 2L2 dL2. Exactly the same as with the L1. I have to use the chain rule on it because L1 and L2 are both functions of X. And on the other side, again, B, right, is just the distance, right, from the river to the town. That doesn't change. That's a constant. The derivative is 0. And then I get the derivative of W minus X. And what's it going to be?
2w minus x times
Times the derivative of W minus X. And W, what was W? Ah, that was the distance horizontally from A to B. So that's constant. Okay? So the derivative of W minus X, well, it's just minus 1. So this becomes minus 2 times W minus X. And so if I solve for dL2, by dividing 2L2, I get W minus X divided by L2. And I can plug that into my equation on top. So I get W. Right. Oh, wait, did I make a mistake? Left out of my, right? This was minus 2, W minus X. So this should be minus. You gotta watch those minuses. Okay, so this becomes minus W minus X over L2. Oh, this isn't so bad because I have X over L1 minus W minus X over L2 equals 0. So I can solve that. So this implies that X over L2 equals X over L1. Or what? All right. So first, let's assume for a moment the second derivative test. We'll do that in a second. Okay, but let's assume we apply it and this is giving us really a minimum. Okay. What does this condition say? Because this looks kind of weird. Okay. If you want to minimize things, then w minus x divided by L2 should be the same as x divided by L1. Is there some nice way that we could encode information? Well, you have two right. When you think right, okay, what's the first thing? Right triangle. I think Pythagorean theorem, right? Okay, but then the second thing you think trig, right? Okay. How can I relate some side to hypotenuse? Well, let's say for instance I look at this angle here and I call it theta 1. This angle here, I called it theta 2. Okay. What's the relation between theta 1, x, and L1? Yeah, cosine, right? Cosine of theta 1 is adjacent over hypotenuse over L1. And cosine of theta 2 is w minus x over L. So what this is saying is that the cosine of theta 2 should be the same as the cosine of theta 1. Now what's interesting about this is when we have where you put B at the same distance away from the curve around A, we said, oh, you should stick it in, right? That should be the, that's what's important, right? Is distance to the point should be the same. But this interpretation, that's actually not how we should have been thinking about it. What's important when you're trying to minimize it, is the angles that you're creating by these lines that are the same side. And that's the important thing. So as you move down A further and away from the river, bring them in, what you make sure is that the cosine you create, that's the key. Distance isn't what you should be looking for. That's not how you're thinking about it. You should be looking at the cosine of these angles. So I think this is a rather nice definition of a typical optimization problem. Okay, let's finish the problem off, because all we've actually done is shown that this condition will either minimize or maximize the situation, right? To make sure we minimize it, let's take the second derivative, it's positive. If you have a positive second derivative at a critical point, then you know you actually had a local minimum. Okay, what was our derivative? Well, our derivative was x over L1 minus w over x over L2. So we want to take the second derivative. So the derivative is just going to be the derivative of the first derivative. X over L1 minus w over L2. All right. And well, it's kind of nasty because we have to use the quotient rule on this. Okay, we'll do it. Low, high, derivative of x is just 1, no problem. High, d low, derivative of L1. Well, let's just leave it as derivative of L1 over L1 squared. Now we do the derivative of this term. So low, d high, derivative of w minus x, which is minus 1. So this becomes minus high d low, that's dl2 dx, over L2 squared. Okay, and we quickly notice you have minus, 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 so we just turn them all into pluses. so this looks at it first. Realize, wait, dl1x, we actually already know an expression for it. X is just x over L1. So I can make this L1 minus, well, x times x over L1 is x squared L1 over L1 squared plus, same thing over here, dl2 is w minus x over L2. So I get L2 plus w minus x squared over L2 over L2 squared. Okay. Now, I could make this L1 squared over L1, so I could turn these into one fraction. Right? Just multiply top and bottom by L1. And then over here, the same thing. It multiplies L2 over L2 and make one. And if I do that, I get L1 squared minus x squared over L1, and then it over L1 squared, so it's the same as L1 cubed, plus L2 plus w minus x squared, squared. The same thing happens. I get L2. Okay, now what I want to show is a positive function. Always positive. That way the second derivative is positive, and so I have a local minimum. Why is this always positive? I feel like I made another minus sign. It was positive. Maybe that should still be a minus. We'll check it. Oh, yeah, that's right. It is a minus, because we left this minus off. There. It doesn't hurt anything. It's still going to be. There we go. Good, good, good. Okay, well, L1, L2 are positive numbers. You cube, no problem. Okay? So the only thing that can make these things negative is the tops were negative. And the tops are always form something minus something. So if you do something minus something, when is it going to be negative? Well, the second something is bigger than the first something. Okay? So could x squared be bigger than L squared? Well, only if x was bigger than L, 1. Right? Can x be bigger than 1? We have a triangle. L1 is the hypotenuse of the triangle. Right? So it's got to be longer than the other two sides. So it in particular has to be longer than x. And for the reason, 2 has to be longer than w minus. Okay, so L1 squared has to be bigger than Lx squared, and L2 squared has to be bigger than w minus x squared. And so this function is always positive. Okay? Which means we can verify using the derivative test that our function is giving us a local minimum. And again, why is it going to be an absolute minimum? Well, the extreme value theorem told us, if you want to find the absolute minimums, you're either going to look for the local minimums or endpoints. Okay, well, let's see what's here. What would the endpoint be? Well, the only endpoint in sight is if x is 0. Now, 0, could you be minimized? Could be minimized? Could it be that you're in a situation? Could you be less than what you get when the angles are equal? That's actually something you have to think about. Okay? The station right here just said, okay, make it as close to A as possible. And you see you'd either go here or all the way down. shorter? Can you make an argument that it can't be shorter?
The distance would be A.
Yeah, this distance would be A.
It's X 0. B is R bigger than A it is. So L2 is B, so it would be bigger.
So you're saying L2, so if you put it here, you have this line.
Yeah.
Okay, and so L2 would be bigger than
A.
A.
Hypotenuse is B.
Mm-hmm.
B is already.
So this line is bigger than B. It's bigger than, but what we're considering is, right, the sum plus this. So, and you're supposed to be, no, I'm not following quite the argument. Okay. Well, here's a shot in the dark. Try at it. This dot here, I mean, it could actually be moved, to a lot of different places, right? You just have a nice function, right? None of the work seems to rely on either of these being positive, in fact. Right? If you took the problem out of the context of the real world problem and just took derivatives of these functions, right, then there would be no endpoints even to talk about. You could have this x be any real number. And if you did that, you do all the same analysis, you get that you had a derivative, you had it being a local minimum, right? Of the second derivative test. Okay, and then that would be it. That would be the whole game, right? There were no endpoints to talk about, and so it would have to be necessarily the absolute minimum. Right? Because the derivative that we're getting, well, it also has to be away from this, which means the length would be going up away. That's why, I mean, if we say it's a local minimum, it means on the other side, it's going up. Okay? And it's actually going to be going up forever. Stop and turn around and do something else, otherwise you get another minimum down the road. Okay? This whole process is one local minimum. Okay, so it really is the absolute minimum. Okay, but let's see. This raises the following point. Through all these calculations, and you get more than one critical point. Maybe you get two critical points. And you do a second derivative test, and you figure out that both of them are local minimum. Then which one is your absolute minimum? Right, okay. You have to test them. The key, right? You have to actually look at it. Okay, and that can happen. Right? You can have a problem that's going to have possibilities for local minimum. And sometimes what happens is you have 5, 10, 20 possibilities. Okay? And then you go and you look at your constraints and you say, oh, wait a second, constraints make it so that even though maybe that is the absolute minimum, I can't use that possibility. Right? Maybe one of them involves, having a negative area of something, or it involves you to live to be 226. Right? Just something bizarre, right? Something that's going to not follow something. Okay, so you have to throw it out and say, okay, fine, I have a bunch of different local minimums to choose from, and some don't make any sense, so I have to throw those out. And now I take the one which is absolute max or min of the remaining ones. Well, I want to write up a problem. Oh, Stephanie, you have a question.
I'm just gonna ask, like, are you a picture or is it gonna be like a word problem? Like,
Both. Both. The problem I wrote is a word problem in that it, uses words. And there's also a picture, which this is not always easy when you're writing things up in language to draw nice pictures, but I was able to produce. Well, let me write up one more problem, and we'll set it up, because we have to do these evaluations today. We probably won't do the whole thing, but I at least want to set it up for you. I think it's a cute problem. So I read in a journal, the guy who wrote it said that the title is wrong. Do dogs know calculus? What's that? And the reason he asked this question, following situation. So he's at the beach. Okay. He's at the beach somewhere, right? Like say, the ocean. And he's playing fetch with Elvis. That was the name. I'm making that up. That was very sweet. Okay, and so he's standing there and he goes, and he throws the ball right into the water, and it lands somewhere in the water. Okay, call that point B. Okay, now we're going to make some assumptions so that this problem is doable. Right? One, we're going to assume it lands in the water. Okay, even though there's waves in the ocean, we're just going to assume it's not move, right? And the wind is not going to blow it or anything. It just stays. Okay, now the dog was standing right next to him, right, when it hits the water. Now the dog is very excited, and so he wants to go get the ball as quickly as possible. Right? He doesn't care about being energy efficient because he's a dog. So he decides, I just want to get there in as short a time as possible. Okay, now, what is the optimal way for the dog to get to the ball if he's trying to minimize the amount of time it takes?
Go straight line.
Go to the straight line, all right? Well, this is water here, and this is the beach. Okay? So this is the edge of the beach. And there's beach, and there's water. Okay? Go into the water, you have to swim. Okay? We'll assume this is significantly deep, that as soon as he goes into the water, he has to swim. He can't for a little bit. Just assume he has to. And if he's on the beach, he can run. Now, what's faster than running? Running, right? Even for Michael, right? You tell him go 100 meters, he's going to beat himself, swimming 100 meters. Okay? An alternative to jumping in and doing a straight line to B, okay, what you could do, you could swim the whole way. You could run down the beach until you get even with the ball. Okay? Run all the way down, then jump into the water and swim to B. Okay, you could do that. Or you might say, well, why do we have to be so extremist? The answer always somewhere in the middle. All right, and you can say, okay, maybe I should run part of the way and then jump into the water and swim to B. So you might be able to stop there. Okay, then jump in. So this is the question is the right way to do it. See if I left out any of my nice picture. Okay. Change some of these things for you. Let's say the distance from, did I give a name to that point? Yeah, we'll call that point C. Say you want to check somewhere in the call that point D. Okay, and well, the distance we should write that. I think I called that when I call it Z. Yeah. We'll call that Z, and maybe we'll call this distance I, and then we'll give a name to this distance. Of course, we already have Z and Y, so what's the distance? Shannon. Z minus Y, very good. Now let's see what we want to do. We want to minimize time. Okay, so we're going to need something else in here. So let's say that my R is equal to the dog speed. Okay, and we assume the dog always runs at a constant speed. Okay, and S will be the swimming. Okay. So let's write down a function for how long it's going to take the dog to get there. Call t for time, and it's going to be a function of how far. Well, I put the y here, the y for technical reasons, I put it here. Okay? And I want to know how far he doesn't go. All right, that's my y. Okay, and if I know what this y is, I can tell you how long it took. Okay, so this will be a function of y. And what is that function? Well, how long it took is how far he ran. That is how long it took him to run it, plus how long it took him to swim. How long did it take him to run? Well, he ran z minus y, runs at a rate of r. So how long did he run for? R times z minus y. Well, R, remember his speed. Okay, so let's say I went 40 miles an hour and I went 200 miles. How long did it take me to do it? Do you do 200 times 40? You do divided by, right? You do divided by. Okay, that's right, because d equals rt. Distance equals rate times time. So time equals distance divided by rate. So the distance that you ran, z minus y, divided by your rate is r. The distance that you swim, right? Well, okay, you swim this distance. I didn't give a name to that. What's my... Do I need to give a name to that? No, I don't. Why? Because, well, I have a right triangle here. Right? And the distance I swim is...
Squared plus y squared.
Is it x squared plus y squared? Square root. The square of the hypotenuse is the sum of the squares of the sides. So that distance is square root of x squared plus y squared. So it's square root of x squared plus y squared divided by my swimming speed. Okay, that's how long it takes. And so I want to minimize y equals z minus y over r plus the square root of x squared plus y squared over s. Let's see. Anything else in there? So we'll write down the constraints. Okay, what are the constraints? Well, the constraints, it's not easy to see exactly what your constraints are. You write down what you know is fixed. Okay? So z is fixed. Okay? So fixed meaning it's a constant. X is fixed. It's a constant. Okay? And then this y you get to choose. Everything else is a constant, which is because it means R and S, by the way, also fixed. This is very nice because it means when you go to take this derivative, well, you only have one variable sitting around. You have y. Everything else, z, r, x, and x, these are all constants. Okay, so you're not going to have to take the derivative of another function to. For every time we did this, on the other hand, we always ended up with another variable that we chain rule on, and we had to use another function, take its derivative, so that we could plug it in. Okay, well, we don't have to do that here. We can actually directly take the derivative and set it equal to 0 with no other to worry about. Okay, okay, so this is where I'm going to stop. Just tell you, right? You set t prime of y equal to 0, solve for y. I'll tell you how far. And then, of course, you have to show t double prime of y is, we want to minimize, right? So we want this to be greater than 0. Okay, and that shows we're actually getting a minimum. Okay. So these are two steps to go and work out.
Would you use the d over dt this time? Like what variable?
So t is the function of y. So you're taking the derivative with respect to, right? T is a function of y. So it's a, that's dependent variable. Y is the independent variable. Okay, so kind of a problem. And I'll just give you a little post to this. At the end of the article, he comes up with the solution. I'll just write up the solution so you can, if you get it, you know you got it. So you get, as your max, y equals, well, there's a couple different ways to write it. So first is x times s divided by the square root of r squared minus s squared. And he writes it in a slightly different form. Another form that you write this as, you divide everything by s, and you can write this as x over r squared over s squared minus 1. Actually, he doesn't write it quite that way, but I found this to be a very nice way to think about things. What he did, he wanted to test what his dog was actually doing, right? How close he was getting to the optimal solution. And so he went out and, now mind you, he had to make, he tried to wait for the water to be very rough. The ball really didn't move a whole lot, and dogs are dogs, so not terribly precise, but he did a scatter plot of his data, and he drew a best fit line. And it turned out that his dog was, with a few exceptions, where the dog just took off and swam, with a few exceptions, the dog actually was getting very close to the optimal solution. And so that's why he asked, does the dog know calculus? Dog intuitively, right, whatever that means for an animal, the dog intuitively knowing exactly what the right point to be jumping into the water. So I thought that was kind of a little story that we had. Okay. If you have more questions, of course, email me. I recommend reading up on this a little bit in the lecture. But now we have to do. We can. Bye bye. We have teaching evaluation.